Welcome to this video on the topic of linear relationships. In this lesson, you'll learn about the parallel and perpendicular line relationships. By the end of this lesson, you'll be able to check whether two lines are parallel, perpendicular, or neither. You'll be able to determine the gradient of parallel and perpendicular lines. And finally, you'll be able to deduce the equation of a parallel or perpendicular line. For this video here, we're going to start off with parallel, and then in the follow-up video, we'll have a look at perpendicular. Jumping into it. Parallel lines are lines that run side by side but never touch. Parallel lines have a common gradient. Two lines are parallel if the division of one gradient by the other equals 1. Otherwise, they are not parallel. Consider the system of equations shown over here. These equations represent three separate lines. The first line is defined as y equals 0.5x plus 2. We can call this line 1. The second line is defined as 0.5x minus 3. We can call this line 2. Finally, we have line 3 that is defined as 0.49x minus 5. What we're going to do is we're going to determine whether there is a parallel relationship between this system of lines or not. To do this, we can use the following syntax. We can say checking, and we'll start off with lines 1 and line 2. So we're checking whether line 1 and line 2 are parallel or not. Now, the first step in doing this is we have to identify the gradients that we're working with. In this case, we can see that the gradient is 0.5 and 0.5 because they're in slope-intercept form, and the gradient is always the coefficient in front of x. Now that I've identified my gradients, I simply state them. So I'll say m1 for line 1 is 0.5, m2 for line 2 is 0.5. Now, checking whether they're parallel or not, what we're looking for is we're looking for a division operation that yields a result of 1. So if I divide m1 by m2 and I get 1, then it's parallel. If I divide m2 by m1 and it equals 1, then it's parallel. Anything else and it's not parallel. So showing this to the reader, I can say m1 divided by m2 is equal to 0.5 divided by 0.5. Now, this calculation is trivial, however, we'll use a calculator anyway. So we say up we come, and then we put it in the calculator just like shown. You can use this on your Sharp calculator just like shown here. I hit equals and I get a value of 1. Now, because I get a value of 1, what this communicates is that we have a parallel relationship here. So this line here, line 1 and line 2, will never touch each other. They will never get closer, nor will they get further apart. They run parallel and never touch. Communicating this to the reader, we can say lines 1 and 2 are parallel. Alright, now that we know lines 1 and 2 are parallel, let's turn our attention to line 3. Now, if lines 1 and 2 are parallel, what that infers is that if line 3 is parallel to either of these two, then it's going to be parallel to both of them. So if 1 is parallel to 3, then 3 is also parallel to 2, and likewise. So what that means is we only have to check for one circumstance. So let's check with lines 1 and 3. Carrying this out, we need to identify the gradient for line 3. Now, because it's in slope-intercept form, we can clearly see it's 0.49. So we simply state the gradients we're working with, to be explicit, 0.5 and 0.49. Now we go for the division. Again, it doesn't matter which gradient's on top, so long as we divide one by another, showing the numbers. Then we say up we come to our calculator. Putting this in, 1.5 divided by 0.49, and of course we see that it's a value that's not equal to 1, and because it's not equal to 1 we can write it as not 1, and therefore this tells us that lines 1 and 3 are not parallel. Now that we've had a look at how we can show the working out to verify or check whether two lines are parallel, now it's your turn. We present ourselves with three systems of equations. So we have y equals 1.5x minus 4 and y equals 1.5x plus 3 and so on. What I'd like you to do is pause the video now and run through the process shown here to determine whether these systems of equations have a parallel relationship or not. So you're comparing whether this line over here is parallel to this line. Once you're done, unpause the video and we'll verify your solutions. Alright, let's have a go. What we can see is that we've got for A, y equals 1.5x minus 4 and y equals 1.5x plus 3. What we should first do is define our equations as y equals 1.5x minus 4. We can say that's line 1 and this is line 2. Now, checking whether they're parallel or not, what we need to do is identify our gradients. So we can see the gradient is always going to be the number in front of the x. Now, writing this out, we say that m1 is 1.5, m2 is also 1.5, and the most savvy about you would notice already that this is indeed going to be a parallel relationship because they're the same. So when we divide one by the other, we indeed get a value of 1. Now, because of this, what we can say is that lines 1 and 2 are in fact parallel. So this was a nice... Okay, let's go to something a little bit trickier. Alright, let's move on to B. We have a system of equations. Our equations are defined as y equals 2x over 5 minus 4. This will be equation 3. And y equals 4x over 10 plus 2. We'll call this equation 4. Now, determining the gradients, we see it's a number in front of x. In this case, it's 2x over 5 or 2x. And the second one is 4 over 10. To be explicit, we write these out. 2 over 5, 4 over 10. Now we step it up a little bit. We determine whether they are parallel or not using the exact same method as the last few examples. So we go m3 divided by m4. And because they're fractions, we can, if we want, we can write it like this. However, the issue of this is it looks horrendous. So instead what we can do is we can say 2 over 5 divided by 4 over 10. Now, it's at this point we can do this in our head by flipping the divisor and multiplying, or we can just use our calculators. In this case, I'll use the calculator. Putting this in a way that will work on your sharp calculators, you open brackets, 2 divided by 5, close brackets, divide, open brackets, 4 divided by 10, close it off. And lo and behold, it's equal to 1. And once again, because this is equal to 1, what we can conclude is that lines 3 and 4 are indeed parallel. Alright, final one, C. We have a new system of equations. Let's see what we get. So, defining what we have a system of equations where we've got y equals minus 3x over 4 plus 3 and y equals minus 5x over 8 minus 5. We will define these lines as line 5 and line 6 respectively. Stating the gradients, we're going to have m5, which is equal to negative 3 over 4, and m6, which is equal to negative 5 over 8. Now checking whether they're parallel using the exact same method as every other time, we're going to go m5 over m6. This will give us 3 over 4 divided by negative 5 over 8. Now because this is looking even trickier, what I'm going to do is what I've done in every other example and say up we come to my calculator, and I'll simply put this in as follows. I'm going to go open brackets negative 3 divided by 4, close it off, divide, and then negative 5 divided by 8, close it off. Now with the negative, it doesn't matter if it goes on the 5 or the 8, so long as I put it in there once, we're winning. Same with the first guy over here. I hit equals, and what you'll notice is I don't get a value of 1 in this instance. Rather, I can say that it's not equal to 1. And therefore, because it's not equal to 1, I can conclude lines 5 and 6 are not parallel. So this has been the process we go through to verify whether our lines are parallel or not. Now let's move on to some trickier stuff. The equation of a line can be determined from 2 known pieces of information. Such information could be 2 points or a point and a gradient. If an unknown line runs parallel to a known line, then you know the gradient. If you know the line passes through a specific point, then you know the line. Now consider, an unknown line runs parallel to the line y equals 5x over 4 plus 2 and passes through point A, 4, 0. What we're going to do is we're going to deduce the equation of a line, or deduce the equation of this line using 3 steps. We're firstly going to determine the gradient, identify the y-intercept, and then finally we're going to deduce the equation of the unknown line. Now the known line that we have is shown over here in purple. We can see it's this line because we've got a gradient of 5 over 2, so we rise 5 and then we go across 4, and then we have the plus 2 for the y-intercept here. Now what we know about our line that we're trying to determine, or our unknown line, is that it passes through A, which is at 4, 0, or in other words the x-intercept, and we know that it runs parallel. So I can draw up a line like that, something like that, and I can make sure that it is parallel, just like that. So instantly I've got a visual cue to work with here. Now that I've got my visual cue set up, let's turn our attention to the algebra that we know up here. Now we've already got our point 4, 0 plotted there, but we turn our attention to line 1, y equals 5x over 4 plus 2. What we know about this line over here, so line 1, is that we have a gradient of 5 over 4. And as mentioned in the question, the unknown line runs parallel. Now if the line runs parallel, then what that means is that the unknown line's gradient m2 must be equal to m1, which in turn must be equal to 5 over 4. So therefore what we know is that for part A, we have determined the gradient where the gradient has got to be 5 over 4 because they're parallel. Now part B, we need to determine our y-intercept. So let's label that A, and we'll go. Now to do this, what we need to do is we need to think of the information that we currently have. We know that we are going to pass through point 4 and 0, and we have a gradient of 5 over 4. Now using this information, what we can do is we can determine the equation. It's going to be determined using the, let's say using the formula y equals mx plus c, or in other words, we can turn it into c equals y minus mx, whereby we're using y1, x1. And because we're going to be using the gradient for this unknown line, we call that m2. Now understanding where we get y1 and x1 from? Well, we're going to use that point up here. So x1, y1. Subbing this information in, we get 0 minus 5 over 4 multiplied by, well, let's write it as 5 over 4 times 4. Now putting this together, I say up we come to our calculator, and I simply put in this expression. So 0, take, open brackets, 5 divided by 4, close it off, open them again, put in the 4, close it, equals. And what you can see is that my y-intercept is now equal to 5. So what we've been able to determine is the y-intercept. So that's at, sorry, -5. Yep. 0, -5. And now what we have is all the information we require to deduce the equation of this line. The equation of this line being y equals mx plus c. We're going to be dealing with m2. So therefore we can write y equals, our m2 in this case is 5 over 4. So we'll go 5x over 4 plus, and we know our c is -5. So we go take 5. So what we've been able to do here is we have been able to determine, or firstly we've been able to determine our gradient simply by taking it from the line that we know we run parallel to. Secondly, we determine our y-intercept. We do this by rearranging our slope-intercept form to solve for the c, so the y-intercept, and we plug in our point A, which we know we run through, and we plug in our known gradient here. Finally, we determine the equation of our line simply by putting the values of m and c into y equals mx plus c, which yields a result of y equals 5x over 4 minus 5. Alright, your turn. Fun 2, you are presented with two situations here. For situation 1, we want to deduce the equation and graph the lines that pass through point A, -5, 0, and runs parallel to the line shown here. So what you've got is another run-of-the-mill question as shown like here. Then secondly, you're going to deduce the equation and graph the lines that has a y-intercept of y int 0, -5, and runs parallel to the line y equals -7x over 6 minus 1. What I'd like you to do is pause the video here, have a go at these, and then when you've had a go, unpause and we'll go through the solution together. Alright, welcome back. Let's have a go at this. What we're dealing with is equation 1 for now. First things first, let's get a visual cue happening. We are dealing with this equation here. What we're going to do is quickly sketch this on the line. We know it has a y-intercept of 0, 1 because it has a +1 at the end here. So 0. Next we know that it has a negative gradient, so it's going to be going downward. And it's going to be going downward at, for every 3 it goes down, it's going to go across 5 because that's its gradient there. So we go down 3, 1, 2, 3, across 5, 1, 2, 3, 4, 5. Similarly, we just extend this backwards, and voila, we have our visual cue. Next piece of information, we know that we are going to cut through the point A, which is -5, 0. So what that infers is that I go to -5, or I go to -5, 0 on my Cartesian plane, so 1, 2, 3, 4, 5, and that is at -5, 0, and I simply get a line that's going to be parallel to that, just like that. Alright, so I've got my visual cues set up. Now we can start doing the algebraic solution here. So what we know is that line 1 has a gradient. Line 1 is defined as -3x over 5 plus 1. which infers that it's got a gradient of m1 equals 3 over 5 and it's negative. Now because these two lines here are parallel, now what that infers is that for m2 it's also going to have a gradient of m equals negative 3 over 5. So that's our gradient done. Next step, we need to determine the y-intercept. To do this, we know that we're going to cut through point A, which is at negative 5, 0, and we've got the gradient of negative 3 over 5. So all we need to do is plug it into the formula c equals y1 minus m2 x1. If you want, you can drop all of these, it's up to you. Alright, next step, what we got to do is we have to sub in our values here. So I'll just do it here and then I'll copy it upwards. Too easy. And then finally I bring up my calculator and I go 0, take, open brackets, minus 3 divided by 5, close it off, open it, minus 5, close it. And thus I get a value of minus 3. So therefore, using the values that I've calculated, y is equal to negative 3 over 5x, take 3, and that's our equation here. And as you can see, cuts through it if I just multiply it. Notice that before it was more of a sketch, so there we see it fits. Alright, so that's A. Now let's set our sights on B. For B, we're dealing with the equation y equals negative 7x over 6 minus 1, and it cuts through this point over here. So let's start off by, we'll plot the point 0, negative 5, and then we will graph the line y equals negative 7x over 6 minus 1. Now I know this one's going to cut at this point here because of the c value here, and we're expecting a negative gradient, so what that infers is that for every 7 we go down, we're going to go across 6. So 1, 2, 3, 4, 5, we'll just put it up here for now, 6, 7, and then we've got to go across 6, so 3, 3, something like that. So now I just stretch it across. Alright, so we've got a rough sketch of our line now. Now what we're expecting to see for the unknown line is that we're dealing with something that looks a little bit like that. It's not exact because I'm only sketching here, but it gives us a bit of an idea of what we're looking for. Alright, so let's calculate. Well, let's deduce this equation this equation for this line shown here using the exact same process we've been doing for the last 40 odd minutes. First thing we're going to do is determine the gradient. In this instance, we're going to say that this one was line 1 and this was line 2. This can be line 3, and therefore m3 in this instance is negative 7 over 6, as I can see that here. So therefore, because they're parallel, it's going to be m4 is equal to negative 7 over 6, just like that. Alright, for the next step we need to determine our y-intercept. In this case it's already told us that it's at 0 minus 5. So it's a nice easy one because we know we're cutting over here at negative 5. We simply know our value for c is minus 5. So therefore, putting it all together, our fourth equation, which runs parallel to our third, is equal to y equals minus 7 over 6x minus 5. Just like that. So in summary, what we had a look at in this lesson was we had a look at the parallel line relationship. So we haven't done this guy just yet. By now you should be able to check whether two lines are parallel or not. You should be able to determine the gradient of parallel lines. And finally, by now you should be able to deduce the equation of parallel lines. Now, if this seemed tricky, then don't worry, that's normal. It's a bit of a lengthy process, but with practice, comes proficiency. What I recommend is that if you found it tricky, practice some more questions. If you found it simple, I recommend you practice some more questions. Again, the reason for this is with practice comes perfection.